DOE CSGF Fellow Kelly Moran in the field of statistics at Duke University.
Hi everyone, thank you for coming to my outgoing fellow talk. I can't believe that I'm already doing this because it feels like just a few months ago I was at my first CSGF program review, but I guess that was about 4 years ago. Today I'm going to be talking about toxic chemicals, but I guess more specifically I'm not going to be talking about toxic chemicals. I'm going to be talking about chemicals that may or may not be toxic. And the problem with figuring out whether or not chemicals are toxic is that it's not always so easy as seeing if something has a radioactive glow. In fact, we're exposed to chemicals in our everyday lives all the time, some of which may be harmful, some of which may not. And I think there's a typical conception that every chemical on the market or that we are exposed to is something that has been thoroughly tested and proved to be very safe. But scarily enough, it turns out that's actually not the case. When it comes to the landscape of chemicals in use today, there's one act called the Toxic Substances Control Act that grants the Environmental Protection Agency oversight on chemicals that aren't in certain special classes, like things that would go in food or drugs or radioactive materials. And at the time of its passage, there was around 60,000 chemicals that were already in use. And these chemicals were grandfathered in and put onto the list of known substances in 1976. And every year since then, there's been around 2,000 or 3,000 chemicals added to the list. So now there's something like 90,000 chemicals on this list of known substances. But the key thing here is that being on that list doesn't mean a chemical is safe. It just means that that chemical is known to be in use. And so what the EPA has to do is they have to retroactively go through and say, okay, we want to look at our list of chemicals, we want to prioritize which chemicals we think might be bad actors. Then for those chemicals, we want to evaluate the risk of those chemicals to humans. And if we find some unreasonable risk, we need to do something about it. The problem with this flow is that it's pretty slow. So going through this process for one chemical, and of course you can do multiple chemicals at a time, but it takes something like 7 to 9 years. And with 80 to 90,000 chemicals on the list of known substances, there's simply not time to test all of them with this very thorough, long process. So how are chemicals tested? And how might we make testing faster? The traditional and considered kind of best, most human-like type of chemical testing is in vivo testing, which means in life. And this is typically things like dosing rats and seeing, if they grow tumors, for example. The faster and a little bit less expensive version of chemical testing is in vitro testing, meaning in glass. This is taking, say, a petri dish or a test tube and putting some substrate in there. For example, say you want to assess how a chemical will react in the brain, so you put some neural cells in a petri dish. And then you put different doses of the chemical in there and see what happens. This can be used to kind of mimic very specific parts of the human body potentially, but it's a little bit harder to extrapolate what happens in vitro to an in-organism study. The fastest and cheapest thing to do is to simply tell your computer to figure out what's going on with a given chemical. And this can be done using kind of detailed mechanistic simulations of how chemicals themselves interact with a given substrate or body part. Or it could be done using some type of statistical modeling. And I'm a statistician, so I'm going to focus on the latter, although I think there's a lot of really cool, interesting work on mechanistic chemical models that could be built into the type of stuff that I'm going to be talking about. The short version of what we're going to do is we're going to learn about distance in chemical space that is relevant to toxicity. And I'll talk more about what that means, but assuming that we do have some measure of distance or similarity between chemicals, we would be able to more quickly design new studies. So for example, we could take a given chemical that is known to be toxic, and we could find other chemicals that are very close to it in this chemical toxicity space, and we could test those. We could increase the efficiency of studies by having to not just include lots and lots of chemicals, but perhaps target our studies to more effectively look at a particular part of the subspace that we're interested in. We can also supplement the results from lab-based studies by using our chemical, our learned distance metric to predict for chemicals that we don't see dose response data for, what our dose response curves should look like, based simply on where in our chemical subspace that given unknown chemical lives. And this will allow us to bridge the gap between the number of chemicals of interest, the 90,000 chemicals, and the number with known toxicological profiles, which varies between a few hundred and a few thousand in ToxCast. So a quick example of how we can use molecular structure as a statistician. And I don't really know how to put a shape into one of my algorithms, so I'm typically more comfortable dealing with numbers as a stats person. So what I first do is I extract numerical features of a given chemical using a software program called Mold2. There's lots of other software programs that could be used to do this type of thing, but Mold2 is just one of them, and what it does is it takes a given chemical structure and returns 777 numeric descriptors of that chemical. This shown example here is BPA. What we can do with this 777 set of descriptors in a very naive way is just say, okay, if these 777 numbers are close to each other, we'll consider a chemical structurally similar. And if the dose response profiles for a chemical are similar, we can consider them similar in activity. And the problem with this kind of naive framework is that we end up with chemicals that are very structurally similar that still are very different in terms of their activity. And this can seem kind of counterintuitive, but the reason for that is, as I mentioned earlier, that the directions of variability in this chemical space, in this space of just all of these numerical descriptors, is not necessarily the variability or the dimension that is most relevant to a given measure of toxicity. So just being similar in terms of those 777 numbers doesn't mean that a chemical is going to be similar in terms of its output. We really want to hone in on what parts of that chemical structure space are important to toxicity. So that's where the modeling piece comes in, the statistical component. There's three key pieces that go into this model. There's factor modeling, which is a way of reducing the dimensionality of your data set by accounting for structured variability. There's Gaussian processes, which act as a prior in function space. So you can think of this as being a probabilistic way to model smooth curves. And we also work with sparsity-inducing priors, which are priors that encourage lots of zeros. And I'll show you how each of those work in this model. A visual model summary shows that we have our two pieces of information. We have our numeric chemical descriptors, here defined as X on the left, and we have our dose response profiles, which are observed as discrete points, here shown as Y on the right. And what we're going to do is we're going to assume that there's some latent subspace, which I'm denoting by eta here, that explains all of the variability in our dose response profiles and also some of the variability in our chemical structures. And then we have this additional set of latent factors, which we're calling nu, that explain the additional variability in our chemical structure that is not related to our dose response profiles. So we're essentially learning where chemicals live in this latent low-dimensional toxicity-relevant space defined by eta, and this latent lower-dimensional toxicity-irrelevant space defined by nu. And how does this allow us to learn about chemical distance? Well, the math notation is not super important here, but the idea is that since we are placing chemicals in this latent toxicity-relevant space, we can define distance between chemicals by looking at the distance in this latent lower dimensional space. And that'll get us similarity in chemical structure that is not necessarily just superfluous structural differences, but it's those structural differences that are found to be important to toxicity. Two chemicals that are very close in this space will have similar dose response profiles and also similar toxicity relevant features, but they might have quite different toxicity irrelevant features. If we were to look at chemical distance or similarity in this learned toxicity relevant space, here I'm showing kind of two similar groups, these light purple, meaning the eta distance is very low for these chemicals, and the bottom left is a kind of inactive area. So this is a region of the chemical space that maps to not particularly active chemicals. And then this middle region is a very toxic region of the chemical space. So BPA lives in this region, as does dimethyl biphenyl A. So a chemical that's quite similar to BPA. And then up on the top right, I'm showing some chemicals that are just kind of weird. So they're far from other chemicals in this data set. And if you remember, when we talked about some of the benefits of this in silico modeling, there's an idea of filling in versus venturing out in the chemical space. So we might say, okay, we know that this BPA region is bad, so we want to test lots of things that live near this middle block. Or we might say, okay, we want to explore other areas of the chemical space that we don't actually know a lot about. So if we were to do that, we would pick 3 super far chemicals in our holdout set of chemicals of interest that we don't potentially have dose response data for. And those would be iodoform, triethyltin bromide, and indeno-123-CD-pyrene, which I've shown here on the bottom. And if we were to predict, for example, for indeno-123-CD-pyrene, we could see that we do have some activity. This is the 95% credible interval for the dose response profile, and then the data credible interval is the lighter gray band around it. And on the bottom, I'm showing just the samples of the AC50 value, which is the model predicted value at which the dose response profile takes half of its maximum. And it's a metric of interest for chemists. And here we have 2 other chemicals that I'm just showing predictions. The blue points are the actual data, which was not used in the model fitting. So these are predicted dose response profiles along with actual observed data. The model also does pretty well for chemicals that aren't activating. Here's just a few examples. On the bottom of the middle, you see acetaminophen, which is Tylenol. So we don't predict much activity, which is good because acetaminophen is not toxic. Okay, so what's next for this model? Using distance to inform mixture models, I also would like to be able to directly specify whether a chemical is active or inactive. The latent low-dimensional space is mapped to the feature space by a linear transform, but some nonlinear dimension reduction could be useful. Of course, the ultimate goal would be linking all of this to human outcomes. And then finally, I've just been looking at one assay and one feature set, but we would also want to be able to include, say, multi-assay outputs and multiple feature sets. What's next for me? I defended my thesis this semester, and I'll be starting a job at Los Alamos National Lab in the winter, which I'm very excited about. I also wanted to mention that this project, I didn't go into a lot of detail about the computing for, but computing in CSGF was vital, not just to this project, but to my whole grad school experience and my career, essentially. My first experience with Gaussian processes, which I used in this project, was through a Lanol practicum, my first summer in grad school. And then through work on this toxicology project, I met a really great collaborator named Matt Wheeler, who was interested in GPs. And because of CSGF, I had the flexibility to say, yes, I would love to work with you. I don't just need to work on my advisor's grant-funded projects. And so with this collaborator, I ended up developing a new fast Gaussian process algorithm. And we'll be able to pull that into this method and expand to bigger applications, and hopefully start working on making this algorithm, the Gaussian process algorithm, more useful for even bigger data sets, which I don't think I would have even thought to do or try to do without CSGF and my experience with computing through this fellowship. So I guess in summary, I just really want to thank the Computational Science Graduate Fellowship, because I would not have had the grad school experience that I had without them. I'm also very grateful to my advisor, Amy Herring, and the rest of my committee, and Matt Wheeler, who I mentioned, who was an excellent collaborator. At Los Alamos, I am very grateful to Earl Lawrence and Dave Ostis, who were two of my summer mentors, and Carrie Myers, who is, I think, just kind of a wonderful career and life mentor. The motivation to finish my PhD came from knowing that the light at the end of the tunnel was getting to work with all of them because they're so amazing. Okay, I think that's all I have. Thank you again, everyone, for watching, and I'm sorry that we can't all be together in person.